Hello teacher, welcome you to my answer report about structured neural network pruning using reinforcement learning algorithms. We'll move to the first part is the background and motivation. The remarkable progress of deep learning and neural network at this moment has led to an increasingly large model such as GPT or vision transformer. However, this large model has a large parameter about several billion parameter, which really hard to deploy on edge device such as mobile phone or smart camera. To solve this problem, network pruning address this issue by removing less important parameter. However, traditional methods often rely on fixed heuristic or require manual tuning for hyperparameter. I propose using reinforcement learning to automate and optimize the pruning process. An R reinforcement learning agent learns to make prune or keep decision on each layer to minimize the parameter of the neural network. As you can see here, our system have three components. The environment is the neural network to be pruned, and in this project, I choose to prune the LANet file on the MNIST dataset. Next one is the RL agent. In this project, we will implement and compare 5 RL algorithm, which is value iteration, policy iteration, Monte Carlos, Q-learning, and SARSA. And last is a reward system, a feedback mechanism that balance accuracy and preservation with the compression efficiency. And to move to the part 3 problem formulation, we will convert the LANet5 model architecture into an MDP progress. The state space will be S, and this is continuous and multidimensional. Our state vector have 8 dimension vector, which is the current layer index, pruning history, current model performance, current compression ratio, state space properties, initial state, terminal state, and all these 8 components will be stored in a vector, which is the state. For action, on the each state or each layer, the agent will choose a pruning ratio from a discrete set, which is 0%, 5%, 10%, 55%, 25%, 50%, and 85%. For each action, uh, specify the percentage of filter or neuron to be removed through the structured pruning. The transition is here for every layer, the transition is 0, and in the last layer, the transition function is 0%. And about the reward function, the reward function balance the accuracy preservation with compression efficiency. As you can see here, uh, my reward function contains 3 components. First is the accuracy drop. the parameter compression ratio, and the computational reduction. Three components here can achieve after the agent action, and uh, the three components here used to calculate the reward function to make the make the agent action better in the next step. To understand about the pruning process, we've moved to the structured pruning implementation. Our structured pruning implementation has three steps. First is the important score calculation. We calculate the important score for each filter or neuron, as you can see here, and then we're choosing the number of filter or neuron to be removed by multiple p with the n total. And after remove the neuron, we have to update the architecture because instructed pruning, after pruning, the removed neuron have to be removed from the architecture. So as you can see here, after prune the convolutional have update from C in C out to C in C X out, and for the fully connected layer, D in D out become to D in D X out. This thing to make sure the removed neuron have removed from the architecture. And for the RL algorithm, we implement value iteration, policy iteration, Monte Carlos, Q-learning, etc. And this is the our algorithm. First, we implement a Q table for all state and action. And for episode 1 to the episode n, we copy the original environment, and we choose action, explore or exploit from the exploration rate. We compute the filter score, remove neuron, and adjust layer. After that, we achieve the reward function and calculate the reward function, and then we update the Q table. For the experiment and evaluation, we will use the MNIST dataset and LeNet 5 to take the experiment. This is the overall result. Sasha seems to have the lowest reward. Next and highest is the Q-learning. And as you can see here, with the baseline, the accuracy is 97%. And with Monte Carlos, the accuracy seems decreased about 6%. And the fraud, but the fraud and the paragraphs have reduced about 50%, which is a really good result. And this is the best pruning policy for each layer, each agent across the layer. Most agents choose to prune 75% from the first layer, and 50, 55% for the next one. And here is the accuracy versus model complexity trade-off. The which the agent appear in the left top corner will be seems to be the best agent. And at this picture, Monte Carlo have high accuracy and low flop, which is really a good result. Uh, Next one is the hyperparameter analysis. With the discount factor, we implement to evaluate is 0.7, 0.8, 0.9, and 0.99. And most agents achieve peak accuracy about gamma equal to 0.9, suggests that balancing immediate future reward is crucial for effective pruning. And this is the um, impact of discount factor on pruning performance. About the learning rate, we compare Q-learning with the SHA-SHA. SHA-SHA seems to be more sensitive than Q-learning, and SHA-SHA is good. SHA-SHA seems good with high SHA-SHA and Q-learning. Both agents achieve the best accuracy and compression with reasonable conversion speed, but SHA-SHA seems more sensitive than Q-learning. About the exploration parameter, we evaluate equity strategy with different configuration is 0.05, 0.1, 0.2, and 0.3. Result here, with Q-learning, the exploration parameter at 0.1 have the highest count accuracy and low highest reward. Monte Carlo with 95% accuracy seem have the highest reward, and SHA-SHA is about 0.05. At the uh, exploration rate equal to 0.05, SHA-SHA achieves significantly higher accuracy compared to other epsilon value. And when epsilon is high, Monte Carlo achieves the best result. This is because Monte Carlo is fundamental an estimation-based method. In the summary of finding, the best agent in this environment is Monte Carlo, achieve high accuracy while reducing 55% of parameter and 43% of the flop. The last part will be conclusion. This report presents an effective method for the network pruning problem using reinforcement learning. Our method automatically learns an optimal pruning policy, outperforming traditional heuristic-based method in balancing accuracy and model size. About limitation and future work, this is a RL model, so it has very high computational cost and parameter sensitivity is the progress of building this environment. I did not fully uh, convert this pruning process into an Markovian environment design. It's still a non-Markovian environment, so which can hinder the conversion and stability of our algorithm. And last is the ineffective reward function for model compression. The reward function may not clearly reflect the balance between pruning amount, model accuracy, and computational cost, which can lead to less effective pruning decision and lower compression performance. Future work, I will improve the state presentation of neural network environment and reduce and redefine the reward function to satisfy the Markov probability fully. Investigate more robust reward mechanism with fewer hyperparameter. Apply the method to tasks beyond image classification, such as neural network processing. We will explore the use of deep Q-learning to enable pruning decision for larger and more complex network and compare model-free reinforcement learning approach like DeepQR with existing on-policy and off-policy methods to identify the most efficient pruning strategy. Thank you for your listening about my presentation.